Welcome. In this lesson, we're going to learn about what is titled the sampling distribution of the sample proportion. And that's a fancy title. And what it's basically getting right to is the idea that if we have a normal distribution, we know a sample size, how many people or individuals we're sampling, we know the success proportion. We want to be able to answer a question that says, what's the chance, if of getting something like, say, 35.7% or more successes if we would expect 34% success. And it's really similar to the previous section we've just been dealing with, where it's a very similar problem, but basically, instead of phrasing and framing the question around the number of successes as a count, so here in the previous section, we do a problem like this. What is the chance of getting 250 successes or more out of 700, right? And so these previous questions were framed as what's the probability or the chance of achieving a count? And now in 6.4, in our current section, we're just basically taking that same concept, but framing the question around what's the chance or the probability of achieving it as a percentage. And so what we're really learning how to do is calculate with z-scores and percentiles and means, but instead of doing all that calculation around a count like 250 out of 700, we're doing that calculation around a percentage or a chance of success. Or I should say, not a percentage of success, but a percentage of the individuals. So 35.7% or more successes out of all the individuals. So how do we do this? The first thing that you really want to realize as you're understanding how to do this is that when we're going to do these two problems right here, is that in theory, they should have the same answer. It's the same question. All we're doing is we're learning how to do these type of problems when it's written as a percentage instead of as a count of successes. 250 total successes, 35.7% successes, same thing, because 250 out of 700 is exactly 35.7. I created these two problems so that they should have the same answer because 250 out of 700 is 35.7. So basically, in our book, this is 6.3. Now we're doing 6.4. So 6.3 is the sampling distribution of sample counts. 6.4 is the sampling distribution of sample proportions. So let's see how to do this. The first thing we're going to do is let's do this original problem kind of as an exercise. And really, I want to do it because I want to make sure that it's clear the difference between 6.3 and 6.4 and also how similar they are. So let's just do this problem straight away, 6.3. And I'm going to go a little bit quickly because it's something we've done in class many times. And there's also so many examples similar to it out there. So let's get right into it. So how would you do this problem? So the question's asking, what's the probability of getting a number of successes, so X is a number of successes of 250 or more. So what is that probability? We're looking for it. Well, that probability, the first thing we would have to do if we're doing this is the chance of getting a certain number is we'd have to convert this count 250 to a z-score. So we'd say this is the same as the probability of having a z value larger than or equal to a certain z value. Now, this is essentially going to be our final work. But first, we have to convert this count to a z-score. So let's do that right now. Remember how we calculate z-score. The z-score for an x value is the x value minus the mean, and this is the sample mean because we're dealing with a sample. So we're not using mu, we're using x bar, divided by the standard deviation for the count. And so this is the standard deviation, which means the typical amount that a count X varies by from the mean. So the standard deviation is the typical amount that a value varies by from the mean. So let's go ahead and use this formula. So we're going to straight away say that The count we're going for is 250 minus the mean. Now the mean, we're going to have to actually do a little bit of calculating here. So the mean would be, how many would we expect? Well, the amount would we expect is the size of our sample times the proportion or the percentage of people that are going to be successful. So the probability of success is 0.34 and the size of the sample is 700. So right here, we're going to say that the number we would expect would be 700 times 0.34. And I already multiplied that. And when you multiply that, you get 238. So we would expect 238 successes. And we're saying, what's the probability of getting 250 or more successes? So right away, we know this probability is going to come out to be less than 50% because, half the time we're going to get more than 238, half the time we're going to get less than 238. So the chance of getting 250 or more would be less than a 50% chance. So let's move along. We got our mean, and now we also need to calculate, of course, our standard deviation of the count. So the standard deviation of the count uses the formula, the square root of the size of the sample times the proportion of successes times the proportion of failures, which would be 700 times 0.34 times and 1 minus 0.34 is 0.66. So we multiply those together, and I already did that and took a square root and got that the standard deviation for the count is 12.53. Now let's pause for a quick second. That value actually should make sense because, if you just think about it, we're basically saying, hey, we expect 238 out of 700. Sometimes we'll get 240 something, sometimes we'll get 220 something. Typically, the count would vary by 12.53 from 238. So we're saying, what's the probability of getting 250 or larger? Now, I actually just want to move this down here. All right, so I wanted to actually move this down here because what I want you to see in a second is how similar all this works when we're doing in 6.4. And I want you to see the little differences so you can really understand 6.3 and 6.4 very well. And if you can do these two sections very clearly and solidly, then you're good for the chapter. So let's continue with this. So our standard deviation for our count was 12.53. And so let's go back up here and let's find our z-score for 250. So the formula is the count minus the sample mean, which is 238, divided by our standard deviation, which we just calculated to be 12.53. Now, this actually ends up being, and I want to continue this down here. This ends up being, excuse me if you couldn't see that, but here it is. It's 250 minus 238 over 12.53. And that actually ends up being, so here's our standard deviation, and now z, finishing our calculation for z, is 250 minus 238 is 12 over 12.53. And when you just finish dividing that, it comes out to be 0.957. And there we go. There's our z-score. Now that's the z-score for a count of 250 out of 700 with a probability of success value of 0.34. So what we just found was that our z value is, and I'm gonna just another color because it's a big deal. We just found it. It is 0.9, and what was it? It was 0.957. Or about 0.96. We'll say 0.957. Now, let's finish the problem. So the probability of being at a z-score of larger than 0.957 is, well, how do you do that? Well, remember when you use this table, I'm going to pull up right here. When you use this table, all these values are the probability of z being less than a certain value. So we have to convert our work to being z more than a certain value. So this just gets rewritten this way. This is literally equal to 1 minus the probability of z being less than a certain value, less than that z value. So the probability of z being less than this value subtracted from 1 is the same as the probability of z being more than this value. And this is a standard thing we do when dealing with z-scores. So let's just finish this up. So this is 1 minus the probability of z being less than 0.957. And our z-score 0.957 is really close to 0.96. And I just rounded that because our table of z-scores goes to 100th place. So let's take a look and let's find this out. 1 minus, what is this value? What is this probability? So let's look up 0.96. So here's 0.9, 0.90, 0.91, 0.92, 0.93, 0.94, 0.95, 0.96, which is right here. 0.83147. So, all right, there we go. That is our probability of z being greater than 0.956. Or I should say, that is our probability of z being less than 0.96. So that is 0.831. And when we finish and just subtract, that comes out to be 0.169, which is approximately 17% chance. And remember what we said at the beginning. The chance of getting 250 or more has to be less than 50%, because 238 is the dividing line. It's the mean. So we would expect half the time there to be more than 238, half the time to be less. What percentage of the time is there going to be more than 250? Well, that's not going to happen that frequently. That's going to happen 17% of the time. Okay, so we just did this entire calculation using counts. What's the probability of getting 250 or more successes? We're going to do the same problem, but instead of looking at in 6.4, now in our new section, instead of looking at it as 250 out of 700, we're going to say 250 out of 700 is just 35.7%. So we're going to delete this little line, even though it's true, because I want you to see how similar this problem actually works out in the end, even though it might not appear that way at the beginning. So what is the chance of getting 35.7% or more successes? All right, we have the same sample size, same probability of success. That's on purpose because it should be the same as this one. Let's do it. So we're asking, what's the probability that our proportion from our sample, and our proportion from our sample, we use p with a little caret, which we call p hat, and p hat being larger than or equal to 35.7%. But I'm going to write that actually as a decimal just to be accurate. So what's the probability of our proportion being 0.357 or greater? So let's calculate. So we're going to have to turn this into a z-score. So what's the probability of z being greater than or equal to whatever the z-score is for this proportion, for this percentage? Let's do it. So how do z-scores work in 6.4 when you're dealing with proportions, percentages, and not counts? X is a count, P as a proportion, or you could think of it as a percentage. So Z in this context, in this type of context, is calculated as the proportion from the sample you're looking for minus the difference between that and the true proportion, the proportion you would expect. Very similar to over here. And then divided by the standard deviation of the sample proportions. And so we calculate this, and we can start to calculate this right now. Let's do it. And we're going to do it really similar. Look at how close this is. And we're looking, and what we're doing is the same thing. We're looking for what is the z-score for 0.357 as a proportion. What's the z-score for that value? So let's do it. So the proportion that we're looking for is 0.357 minus the proportion that we would expect. Now, what proportion would we expect? Well, we would expect the true proportion in the population, which is 0.34. So this is 0.34. And then we would divide by the standard deviation of the proportions. Now, calculating the standard deviation for the proportions is a story in and of itself. And I went over this very briefly in class a little bit ago before we went on spring break, but I'm going to go over it again. How do you find the standard deviation for the proportions? Let's understand this from the get-go. The standard deviations for the proportions is essentially the standard deviation for the count, but when you want to turn a count into a proportion, you divide by n. So we're going to take our normal standard deviation and divide by n. Now, our normal standard deviation is the size of our sample times our proportion times the proportion success, or the percentage of success times the percentage or the proportion of failure. So same thing. Now divided by n. Now let's continue to calculate this. How can we simplify this? And actually this formula right here would work. We could just leave this as is, and it would work as a formula for the standard deviation of the proportions that we need in our z-score calculation above. However, we want to simplify this, and what appears in the book is a simplified version. What will appear in future statistics courses is a simplified version. So the trick to simplifying this is that you basically want to turn this n into having a square root. So the top already has a square root. The bottom, you want to have a square root. So the way you can make something have a square root is you basically square it, and then because a square is the opposite of a square root, that allows you to put a square on it and maintain it as identical. So this is n is equivalent to the square root of n squared. So all you do if you want to put a square root on something but not alter its true value is you also put a square on whatever it is. If this was a bunch of stuff or a larger term, we could say, we would put a parentheses and then put the square like that. And whatever was in there could be a larger expression that could work the same way. Okay, so now, because these both have square roots, we can simplify them together into one square root over n squared. And now I hope you realize that this n cancels with one of the n's from the bottom and from the denominator. And we get that p, the probability of success or proportion of success, times the proportion of failure divided by n. That is the formula for the standard deviation of the proportion. Okay, we use this to calculate the standard deviation, and let's do it. So we're going to take this formula and we're going to pop it up right here, and we're going to use it. So the standard deviation of the proportion would be, and let's write the formula just as I wrote the formula here. That's p times 1 minus p divided by n with a square root. And so this would be the standard deviation of the proportion would be our proportion of successes times our proportion of failures divided by our number of size of our sample, which is 700. And I already calculated this. Square root goes for the whole thing. And the value comes out to be 0.0179. So our standard deviation of proportions is 0.0179. Now, just why is this so much smaller than this? Well, they reflect the same situation, but this is like you're counting whole individuals. And here you're dealing with percentages. So this is saying that the typical sample will vary from the average sample by 0.017, or about 1.7%. And that kind of makes sense, because if you think we're going to expect 34% on average, the typical sample will vary by about 1.79%. That's what standard deviation measures. So let's do it. Oh, what do we still need though? Just as we needed the mean here, we need the proportion here. Ah, well, that's actually so easy. The proportion that we would expect would just be exactly what's already in the problem, so 0.34. And that's why that went right there. Here we had to calculate 238 a little bit by multiplying 700 times our probability of success. Now we're ready to finish this up. And so the standard deviation that we just calculated from our work right here using our formula of standard deviation of proportions is 0.0179. Now, let's finish calculating this z-score down below. All right, so that was 0.357 minus 0.34. So z equals 0.357 minus 0.34 divided by that standard deviation we got, which is 0.0179. So let's calculate. Actually, I want to do this using the exact same formatting. So this might seem strange, but I'm going to do the same calculation, but I want you to see. Let's subtract these up here. Let's do the work. Let's subtract up here before I rewrite it down here. So 0.357 minus 0.34 is 0.017. So the top there, subtracting those, is 0.017, and the denominator is 0.0179. So let's divide that. When you divide 0.017 divided by 0.0179, what do you get as your z-score? 0.957. And now it's actually the same problem. But to see that, you had to understand how to calculate standard deviations with a proportion. All right, and that means you had to understand the concept of that we're dealing with is proportions and not counts. So the rest of the problem is actually identical, and I'll just do it anyway, even though it might seem like a formal exercise. The probability of z being greater than 0.957 would mean, well, we convert that to 1 minus the probability of z being less or than or equal to 0.957. And we round that to be hundredths because our normal table likes z values that are with hundredths. And what's the probability of z being less than or equal to 0.96? Well, just for the sake of it, let's go right back here. 0.91, 0.90, 0.91, 0.92, 0.93, 0.94, 0.95, 0.96. Boom, right there. 0.8314. So 1 minus 0.831, which is about 0.169, which is approximately 17% chance. So there's a 17% chance of getting 35.7% or more successes in this scenario. And the key to understand is that we use this different way of calculating a z-score using a proportion. This work over here is the key work you want to review. When you're doing this problem in general, this is the derivation of the formula. You're not going to do this work every time. You'll probably just jump straight to that step and use that formula straight away. However, professors and teachers love to use questions or put questions on quizzes. Where does this formula come from? Well, you want to be comfortable kind of recreating these steps. Okay, now let's do one more quick example just to make sure that this is clear. Example 2. Let's take a fresh problem. Let's say it's known that within a certain city, 14% of adults play a musical instrument. Ah, there's like our probability of success. If you randomly survey 200, that's like our n, the size of our sample, What is the probability that 16% or fewer will play an instrument? Now, I hope you realize that this is likely to happen. We're going to get probably more than 50, we're going to get for sure more than 50%. Because if you think about it, half the time we're going to get less than 14%. Half the time we're going to get more than 14%. What's the chance of getting 16% or fewer just under that bar? Well, more than half the time. All right, so let's calculate. So what are we going to do? We're going to just go ahead and just straightforward use the formula. So we have our, whoops, not our marker anymore. We have our probability of success in the population. We would expect a proportion of 14.14, proportion of 0.14 or 14% of people, adults, to play an instrument. The proportion that we're looking to achieve is 0.16 or lower. We want to know what's the probability of that. And our n is, of course, 200. So we're saying, what's the probability of getting a proportion less than or equal to 16% or 0.16? So let's do it. We're going to convert this to a z-score. What's the probability of z being less than or equal to a certain value? And our last step is going to be to write this value in and go to this table and look it up. But let's calculate our z-score. What's the z-score for this proportion? So our z-score is going to be well, the proportion we're looking for minus the proportion we would expect divided by the standard deviation of the proportions. So the proportion we're looking for is 0.16. The proportion that we would expect would be 0.14. So the proportion we're looking for is 2% higher than what we would expect. Now, this standard deviation of the proportion, we're going to have to calculate right now. So let's do it. The standard deviation of the proportion is equal to the square root. And see here, we're just going to straight use the formula, which is P times, or proportion times one, proportion of failures. I should say proportion of successes times proportion of failures divided by the size of the sample, all with the square root. All right. So this is 0.34 times 0.66 divided by 200. Oh, that's the previous problem. Silly me. Silly me. What is this? This is actually 0.14. And you know what? I'm sorry. I calculated this earlier. We're going to change this. What's the probability of getting 17% or higher? So even a higher percentage chance. So we're likely to fall at 17% or under. So let's change that to be 0.17. The reason I actually changed it from 0.16 to 0.17 is because it's a little bit further from 14. And I wanted you to just see that. All right, so this is 0.17. All right, and this is also 0.17. So what's the chance of getting 17% or fewer adults who play an instrument if the chance of somebody playing an instrument is 14%? So, all right, let's do it. So it's 0.14, that's the chance of success, times the chance of failure. Now, be careful, don't just put 0.17. That's a noob mistake. You want to really make sure that you put the chance of failure right there. And the chance of failure is 1 minus this probability, which would be 0.86 divided by 200. Now, calculating that, that is 0.02453. That is the standard deviation for the proportions, which means the typical proportion varies by about 2.4% from 14%. Okay, now that we have our standard deviation, we can go and finish the calculation for our z-score. So this is going to go right in here, and that is 0.02453. 453. So subtracting the tops is 0.03, the numerator, subtracting the tops, the numerator, and then dividing by the denominator produces a z-score of 1.22. So in this context, a percentage chance, or not a percentage chance, but a proportion of 0.17 or 17% of individuals represents a z-score of 1.22. Now, let's go look up that z-score. What's the probability of getting a z-score of less than or equal to 1.22? Well, now we just turn to our table and we look it up. So 1.22, here's 1.2, 1.20, 1.21, 1.22. 88.8 or 88.9%. Okay. So this is 0.889, which is approximately 89%. So there is an 89% chance that 17% or fewer adults out of 200 will play an instrument. So there's an 89% chance that 17% or fewer adults out of 200 will play an instrument. So what's the chance that you take 200 adults and 17% of them or fewer of them will play an instrument? Well, that's likely to happen. 89% of the time, you're going to get 17% or fewer. Why is this percentage so high from a common sense understanding? Is because on average, the average sample is going to have 14%. On average, we would expect 14% of the people to play an instrument. So what's the chance that 17% or fewer play? Well, that's likely to happen because you're usually going to get about 14%. And doing our calculations, we see using z-scores, using our standard normal table, this wonderful thing, we can calculate that the z-score is 1.22 and the probability of being at that z-score or lower is 89%. So I hope this was helpful. I hope this helps you with the homework. I hope perhaps you have a question that you feel comfortable asking in class. And I'll see you soon.